Entropy is a thermodynamic state function that measures the randomness or disorder in the system. That means that if the system has higher order, it will have lower entropy. Or if it has a higher degree of disorder or randomness, it will have higher entropy. And since it's a state function, it's going to only depend on the entropy of the final state minus the entropy of the initial state. And if the process of interest is increasing randomness in the system from the initial state to the final state, that will mean a positive change in entropy. Solid state, for example, is a more ordered state where the atoms or molecules in the structures are locked into a specific locations as compared to the liquid state, which has much more randomness in the position of the molecules, and the gaseous state, which is even more random in the position of the molecules. So as you move from solid to liquid to gas, you're actually increasing the randomness in the system or increasing the entropy in the system, which means a phase transition from the solid state to the liquid state, for example, is a positive change in entropy. To explain the relationship between entropy and randomness in the system, let's go through this discussion here. So we define any specific way to describe the arrangement of the system or of the energy of the system as a microstate. So for example, if you try to put 4 numbers in the left-hand side of this tile and leave the right-hand side empty, there is only one way to do this, which is the one shown in the picture here. So this system here has one way to describe or one microstate. In contrast, if you try to put 3 numbers on one side and 1 number on the other side, you will have 4 different ways to do it, as shown in the figure right here, where you put 1, 2, 3, and put 4 on the other side, and then switch one of the other numbers each time. So that will give you a total of 4 ways to do this, or to describe the system in this case, which means the system has 4 different microstates. So it has higher number of microstates. If you try to put 2 numbers on one side and 2 numbers on the other side, you will have 6 different ways to do it, as shown in the figure right here. So if we define the number of microstate as W, the entropy of the system is going to be defined according to this formula here, to be proportional to the natural log of the number of microstates describing the system. And based on that, and since entropy is a state function, the change in entropy is going to be the entropy of the final state minus the entropy of the initial state. And if we substitute for the definition of entropy in this formula right here, the change in entropy is going to be proportional to the natural log of the ratio between the number of microstates in the final state and the number of microstates in the initial state. So if the final state has higher number of microstates or higher randomness than the initial state, then this ratio here is going to be larger than 1, and this will make the change in entropy value a positive value, and vice versa. If the number of microstates in the final state decreased, that will make the ratio less than 1 and will make the value for the entropy change smaller than 0 or a negative value. When you start with solid state, is going to be much more ordered state than liquid state. So when you move from solid state to liquid state, you are moving from an ordered system to a much less ordered system, or a much random system. And this change here will have a positive change in entropy, right? And same thing when you move from the liquid state to the vapor state. Again, you're moving to a much random system or a much less ordered system. So the entropy in the vapor state is much higher than the liquid state. that makes the change in entropy positive. And same thing will happen when you dissolve something, because you're moving the system from a ordered solid state to a much random solution with the molecules of the solute much more free to move around randomly. So that's again a positive change in entropy. And same thing will happen when you heat up something, because as you heat up substances, you're actually increasing the vibration motion of the component ions or molecules, which means it's much more random in position for each of the molecules. So you're increasing the randomness in the system. So that makes the heating a positive change in entropy. So that takes us to the third law of thermodynamics. So at 0 Kelvin, a perfect crystalline substance will have only one way to describe, because each atom or molecule in the structure will have a very restricted location or position. So there is only one way to describe it, only one microstate. If you put the value for microstate to be 1 in the formula here, that will make the entropy 0. So that's exactly the statement of the third law of thermodynamics, is that any perfect crystalline substance at the 0 Kelvin degree is going to have 0 entropy, because it has only one microstate to describe it. And as we said, heating anything is actually increasing the randomness in the system, because it increases the vibration in the system. So that will increase the entropy as you heat up the solid till you reach the melting point. And melting is going to be another increase in the entropy, because you're moving from the more ordered solid state to the less ordered liquid state. And then when you heat up the liquid, that increases the motion of the molecules in the system. So that's again another positive increase in entropy till you reach the melting point. And the melting is another increase in entropy, another process with increase in entropy, because you're moving the system from a more ordered liquid state to a much less ordered or more random gaseous state. And as you heat up the gas, that's again a positive increase in entropy, because you increase the randomness and the speed of the random motion of the molecules in the sample. So based on these concepts, we can actually make predictions about specific physical processes as melting or evaporation. So when you evaporate a sample from the liquid state to the gaseous state, again, that's a change from a more ordered system to a much less ordered system or more random system with more entropy. So that's a positive change in entropy. Same thing if you move from the solid state to the gaseous state, you're moving to a much more random system with much higher entropy. That's a positive change in entropy. And we can use these concepts to make predictions about different processes. So freezing a sample of ethanol, for example, is a change from the liquid state to the solid state, right? So that is a change from a random system to a much less entropic or less random system. So that's a negative change in entropy. In the second case here, if you evaporate a beaker of liquid at room temperature, so that's an evaporation process, which means it's a change from the liquid state to the gaseous state. You're actually making the sample much more random, or has much higher entropy. So that's a positive change in entropy for the sample. If you dissolve a substance in water, you're actually moving this substance from solid to a much more random solution with much higher entropy. So that's again a positive change in entropy. If you cool something down, you're actually decreasing the motion of the molecules in the structure or in the sample itself. So that means you're decreasing the randomness or decreasing the entropy in the sample. So cooling is a negative change in entropy. The same concepts can be applied to chemical reactions, and we can determine the entropy predicted for chemical reactions based on the physical states of the products in comparison to the reactants. So if the reaction is producing more moles or molecules of gas than it consumes, so that's a positive change of entropy for this reaction. If the opposite happens, if it produces less number of gas molecules, it's actually a negative change in entropy. If it produces the same number of gas molecules as it consumes, then you cannot make a prediction about the sign of entropy change in this case, but you can predict that it's going to be a small change in entropy. So let's apply these rules to these examples right here. If you look at example 1, the reaction is actually starting with 2 moles of this substance, 1 mole of this, so that's a total of 3, and it produces 2 moles of the product. So what happened is that the number of moles changed from 3 to 2, so less number of moles, the system is actually getting more ordered or less entropic, so that's a negative change in entropy. For the second reaction here, you're moving from the solid state to the gaseous state. As you said, solid state is a much more ordered or much less random system as compared to the gaseous state, which is much less ordered or much more random. So you're making the system more random, so you're increasing the randomness or the entropy in the system with a positive change in entropy. If you look at the last example here, you're consuming gases and producing gases. So there is no physical change happens. In terms of the number of moles, again, it's the same number of moles that you start with as the number of moles that you end up with. So we cannot make prediction about the sign, but we can predict that the magnitude is small, as we said in the previous slide. So for example, in this chart right here, can you make predictions for the sign of each of these processes here? If you look at delta S1, this corresponds to a heating of a solid sample to a higher temperature. And as we said, heating increases the vibration in the sample, which increases the randomness or the entropy of the sample. So you expect delta S1 to be positive. This delta S2 is melting, so it's a change from the solid state to the liquid state. Liquid state is much more random system, much higher entropy, so that's again a positive change in entropy. Delta S3 is heating for the liquid, so again, heating is a positive change in entropy. Vaporization would produce a much more random gaseous sample, so that's a positive change in entropy. Delta S5 corresponds to heating the gas. Heating is a positive change in entropy. Delta S6 is a change from the gaseous phase to the solid phase. So you start from a random state, you end up with a much more ordered state. So you decrease the entropy of the system, so that's a negative change in entropy. So all of these are positive except delta S6.